Hello everyone, myself Dr. Kadamri Agrawal, Associate Professor in Department of Computer Science and Engineering, and today I am going to discuss the order of group in discrete mathematics. It is one of the important topic of the discrete mathematics. So the order of the group can be defined as number of elements present in the group. Suppose the group is having the 4 elements, then its order will be 4. And definitely the order of a group can be finite. If the group is finite, then we can find the order of the group. If the group is infinite, then its order will be infinite. For example, this is particular group in which there are 4 elements, 1, minus 1, iota and minus 1. This is a cube root of unity group, and here we can see that there are 4 elements, so its order will be 4. The next one is how we can find the order of particular elements in a group. Suppose the group is having 4 elements and we want to find the order of particular element A in the group, then how we can find this? So we can define the order of an element A in the group G is the smallest positive integer n. It is n such that A raised to the power n is equals to E. Means we have to find the part E such that we are getting the identity element of the group. For example, if we want to find the order of every element of the multiplicative group 1 omega and omega square, this is a group having 3 elements. The order of this particular group will be 3 definitely. Now we want to find the order of each and every element of this group under multiplication operation. We all know that under multiplication, the identity element is 1. So what should be the power of each and every element such that we can get 1 will be the order of that particular element. Order of 1 will be 1 because the 1 power 1 will be 1. Order of omega will be 3 because we know that omega cube is 1. So we are getting identity element when the power of omega is 3. So that power will be a order of the element. Similarly, order of omega square will be 3 because 3 into 2 will be 6. And if the omega cube is 1, then omega 6 will also be 1. The next example is we have to find the order of every element in the multiplicative group 1 minus 1 iota minus 1. And there are 4 elements. So this is a multiplicative group. That means it is a group under multiplication. And so we have to find the order of each and every element, and the identity of multiplicative group is 1, that we know very well. So the order of 1 will be 1 and order of minus 1 will be 2 because minus 1 raised to the power 2 will get 1. So order of iota will be 4 because we know that iota square is minus 1 and minus 1 into 1 is minus 1 into minus 1 will be 1, so order will be 4. Similarly, order of iota minus iota will be 4. The next example is we have to find the order of every elements of the multiplicative group G. Here we can see that there are 6 elements in the group A square, A cube, A4, A5 and A6. Here the identity is defined at A raised to the power 6 is equals to 1. Means we are getting the identity element at power 6. So now we can find the order of each and every element. Order of A will be 6 because A raised to the power 6 is 1. Order of A square will be 3 because it will become order of A6 and which is 1. Order of A cube will be 2 because A cube into A square will be A6 and A6 is 1. Order of A4 will be 3 because it will become order of A raised to the power 12 and A raised to the power 12 will be 1 as A raised to the power 6 is 1. Similarly, order of A raised to the power 5 will be 6 because 6, 5 the 30 and 6 A raised to the power 6 is equals to 1. So A raised to the power 30 will also be 1. And order of A raised to the power 6 is 1. It is already given. Now the next important topic is cyclic group. A group is called a cyclic group if for some element A that belongs to that group, every element of G is of the form A raised to the power n where n is some integer. Means we have to represent each and every element of the group in a single element power form. Means we have to find a one element in which we can represent the complete group in its power. Then in that case the element will be called as a generator of G and G will be called as a cyclic group and A will be called as a generator, denoted by G is equals to bracket A, and it will be represented in the form of powers. For example, the multiplicative group G is equals to 1 minus 1 iota minus 1. We have to prove that this group is a cyclic group. This group is having order 4, and this is called cube root of unity group. There are 4 elements, and we have to check whether this group is a cyclic or not. This group will be a cyclic group if we are able to find one particular element in which we can represent all the elements of this group. Means all the elements of this group can be represented in the form of one particular element. So this is possible in this case because we can represent all these 4 elements either in the form of iota power or in the form of minus iota power. For example, one can be represented as iota 4, and minus 1 can be represented as iota square. Iota is iota and minus iota is iota cube, because iota square is minus 1 and minus 1 into iota will become minus iota. So we can easily represent all these 4 elements of a group in the form of iota power. Hence we can say that this group is a cyclic group and iota is a generator of G. Similarly, minus iota is also a generator of this group. The next example is fourth root of unity group. The multiplicative group 1 omega omega square is cyclic. We have to prove whether this group is cyclic or not. This group is a cyclic group because we can represent all the elements 1 omega and omega square either in the form of omega and omega square, because we know that omega cube is 1. Hence 1 can be represented as omega cube. Similarly, we can also represent omega and omega square in the form of omega. And the next example is we have to show that 1 and 5 are generator of cyclic group G plus 6. This is plus modulo 6 operation. Means we have to plus the two variables, then we have to take the modulo division. It is represented as plus modulo 6. And the group is defined as 0, 1, 2, 3, 4, 5. There are 6 elements from 0 to 5. Now, we have to check whether this group is a cyclic or not under the operation plus 6, and the generators are 1 and 5. So 1 raised to the power 1 will be 1, and 1 raised to the power 2 will get 2, because it is not 1 raised to the power 2. It is basically a 1 and second 1, and in between there is a operation plus 6. So 1 plus 1 will be 2, and modulo 6, 2 modulo 6 will be 2. Similarly, 1 raised to the power 3, it is not exactly the 1 raised to the power 3. It means 1 plus 6 1 plus 6 1. Means we are writing 1 3 times and we are taking this operation plus 6 between 1. So every time we'll add it and we'll take the modulo division and we'll get the 3. Similarly, 1 raised to the power 4 means 1 plus 6 1 plus 6 1 plus 6 1. In that case, we'll get 4. So here we can see that we are getting each and every element of the group with the help of one power under the operation plus 6. Hence, we can say that 1 is a generator of this group and G under operation plus 6 is a cyclic group. And these are few very important properties of the cyclic group. Every cyclic group is an abelian group. Definitely, the cyclic group will be abelian group because it will satisfy the property of commutativity. And second important property is if A is the generator of cyclic group G, then A inverse will also be a generator of the G. And third important property of cyclic group is every group of prime order is cyclic. Means if order of any particular group is, that is number of elements are in prime number, then that will be a cyclic group. Every subgroup of a cyclic group is also a cyclic group. And we can easily prove these statements. For example, every cyclic group is an abelian group. In this, we can take a G be a cyclic group, which is generated by A, and we take X and Y be the two elements of the G, then there exist integer R and S such that we can represent X and Y in its power. That is A raised to the power R and A raised to the power S. Now, as per the commutativity X into Y, that will be equal to A raised to the power R and A raised to the power S. If the bases are same, then powers will be added. It will become A raised to the power S plus R. And A raised to the power R S plus R further can be split in A raised to the power S, A raised to the power R, which is equals to Yx. Hence, xy is equals to Yx. It is following the property of commutativity. Hence, we can say that x and y belongs to G. Therefore, G is a abelian group. Next one is every group of prime order is cyclic. The G is a finite group whose order is a prime number P, and G is a group of prime order. G must contain at least two elements because 2 is the least positive prime. Then there must exist an element A which is belongs to the group. Then A must not be equal to the identity. Because A is not the identity element, then definitely order of A will be greater than and equals to 2. And we assume that order of A is M. If H is a cyclic subgroup of G generated by A, then order of H is equals to order of A is equals to M. By Lagrange theorem, M must be a divisor of P. Hence, with the help of Lagrange theorem, we can easily prove that every group of prime order is a cyclic group. And these are the references, Swapan Kumar Sarkar and Shom series of discrete mathematics. Thank you everyone. If you like the contents, kindly like and subscribe the video.